All right, so let's start. Last lecture we were looking at some of the important characteristics of amplifiers, and what is next is that we would start and building meaning analysis and design of basic amplifier building blocks. And as we said that towards the end we'll try and integrate them and make an operational amplifier. Now, before we do that, we need a little bit of discussion, a couple of lectures of discussion related to models, device models, meaning models for PN junction diode, bipolar, and MOSFETs. And so what we'll do is in today's lecture is something that you've probably seen in ESC201, which is small signal model. But it's a very important concept, so we'll go over it once more, perhaps in a little bit more detail. And we found that over the years that this is a major source of confusion. This is something that, the distinction between a small signal model, an AC model, or a large signal model is not often very clear. So let me go over what this concept is, and you'll see how important this is over the rest of the course here. So before that, in general, when we do circuit analysis, what we are doing is basically whatever circuit is given to us, we're taking the circuit and using our techniques of KVL, KCL, and we transform that particular circuit into a set of mathematical equations. And then we solve those mathematical equations to get the voltages and currents and power and whatever you want, right? So, for example, a very simple circuit that is given here, analysis means taking this particular circuit, converting it into equations. Once you get a set of equations, it becomes more of a mathematical problem, solving those equations, okay? So if we take this particular circuit here, what we do, of course, is, as you can see here, we write down Vs is I times R plus Vd here. This is a single loop circuit. And let's say we are interested in this output voltage Vd here. We need a model. In fact, when we write this equation, if I were to be very general, I would have written application of KVL would have given me Vs here equal to VR, voltage drop across the resistor, plus the voltage drop across the diode. So a more general description would have been Vs equal to VR plus Vd. Now to proceed further, I've already applied KVL. So KVL is over. To proceed further, I need model, which I've already used. That the model of a resistor is, the drop across the resistor is I times R. So we've already used the model of a resistor. Now to proceed further, I need the model of the diode here. And which we'll see later, which you're already familiar also. One of the descriptions of the diode is that the diode current varies exponentially with the diode voltage here. So that's a model here. Once I have this ID as a relationship of VD, now you know that Vs is known, and I can take this VD here and express it in terms of ID. And we also know from KCL that whatever current is flowing here is the same as the current flowing here. So you do that, and then eventually you get a simple mathematical equation. Not that simple because it's nonlinear, and then you solve it and you get the answer. The point is that analysis starts with application of KVL and KCL, but then after that you have to apply the model of a resistor, model of a diode. Once you apply the model, then you have a complete mathematical description of the circuit, and then you solve those equations and you get the answers that you are seeking. Okay, so models are obviously important, and your analysis, as you can see, will be as accurate as your models are. For example, if you're using an element and you're modeling it as a resistor, right? That element may not be a pure resistor. It may have a little bit of inductance in it. It may have a little bit of capacitance in it. So if your model is simplistic, if you're modeling it simply as a resistor, then your analysis is, the results of the analysis would not be that accurate here. So the results of the analysis depend on how accurate your models are. Okay, so the models are very important. Now, obviously, we can build very accurate models. We can build very accurate models, and as you would appreciate, that as you build more accurate models, the mathematical description of that particular model becomes more complex. The equations become more complex. And therefore, so one of the price that we have to pay is that when we make the model accurate, our equations become complex, which makes the analysis difficult. The numbers that I'm seeking for current or voltage or whatever, it becomes difficult. So that's the price that you have to pay. You can use a very accurate model, but the accurate model is also complex, and which makes the analysis also complex. Not only that, it not only makes the analysis complex, but the results that you get from the analysis. The results that you get from the analysis would also be a complicated expression. Now, at the end of the day, you have to ask, why are you doing the analysis? What is the goal of analysis? Is it just a number that you're looking for? A number for the current? Is it all that you're looking for? What is the goal of analysis? Yes, number is a part of the story. I want to know how much current is flowing. But the numbers, as we'll have a more detailed discussion perhaps in the next or the following lecture on what are the goals of analysis. But number is part of the story. If you're just looking for a number, I can take this particular circuit and I'll show it to you. I can put it into a computer simulation program, circuit simulation, and the circuit simulator would give you a precise value of the current. Would give you a precise value of the current. All of you went through the tutorial yesterday, and we gave you it was not a very complex circuit, and we'll get it graded. The assessment, my initial assessment is probably something like maybe less than 10% would have gotten it right. Less than 10% of the students would have gotten the final answer right. Okay? But you give the same circuit to a circuit simulator. Circuit simulator would give you a precise value of the answer. Right? So if I'm just looking for a number here, a circuit simulator would do a far better job than what you guys can do with a far more complicated circuit. Okay? So it's not just a number that I'm looking for. A greater numbers are a part of the story, but a greater reason why I'm doing this why I'm doing this analysis and trying to get an expression and all that is, through the analysis, we are seeking to understand. We are seeking to understand the circuit. It has a certain behavior, and we are seeking to understand why it behaves in a certain way. Okay, it's not just numbers are part of the story, but understanding is the greater objective. You want to understand how this particular circuit works. Now think about it. If I use a very complicated model, first of all, analysis will become complex. It will take a lot of time, and analysis would also become error prone. You'll make errors in the analysis. The final expression that you get would also be complicated. Would be a big mathematical expression. And a big mathematical expression, we can get it. When you look at it, you won't figure out what is really going on. For example, if we are interested in finding out how does my current I depend on, let's say, Vs, or depend on R. If you have a complicated expression, while looking at the expression, you will not understand what the dependence on I on R is. So you'll get a precise answer, but you will not understand very well what the circuit is. So that's the price that you have to pay for complex model. Analysis becomes difficult. Analysis becomes error prone, especially when you do it manually. And the results that you get are hard to understand. On the other hand, if I use a simple model, as all of you know, you've done the analysis in your previous exposure to this particular circuit, many times we don't use this model. What do? We approximate the diode by a sort of a battery of 0.7 or 0.65 or whatever, and we use that particular model. That model is simple but inaccurate. When you make something simple, you're obviously losing information there. You're making it inaccurate. But the answer that you get, you'll get an expression which is simple. Simple but inaccurate. right? If you try to use that particular model and try to calculate the value of the current will not be accurate because you've simplified the model. A diode is not really a 0.7 volt battery. A diode's characteristics is exponential in nature. So once you simplify the model, obviously you're losing accuracy, and the result, the value of the current that you'll get will be inaccurate. But what will you get? You'll get an expression which is simple. And the simple expression would help you understand how does my I depend on R, how does my I depend on something else. It would help in building understanding. So if you're looking for building understanding, then we use simple models. The purpose is different for those simple models. They build understanding, they help you understand how your circuit works. They'll give you an approximate value of the currents and voltages, right? So that's the starting point. If you're looking for more precise values of currents and voltages, then there are other ways of doing it. Especially, we'll go and we'll tell you how you can use circuit simulators and you can get more precise values. So in that context, what I'm trying to emphasize is that we need simple models. We need simple models. They have a very important role. They may give you slightly inaccurate answer or more inaccurate answer, but they'll help you in building understanding of the circuit. And in that context, this incremental or small signal models are important. In practice, for example, if I have an equation like this, in theory, if I have an equation like this equation is enough to analyze any diode circuit. But other models that we use and deploy, we do it for the purpose of simplifying circuit analysis here. Okay, so let's look into what this concept of small signal model is, which we will use it throughout this particular course here. Small signal model of a diode, small signal model of a BJT, small signal model of a MOSFET. So where is this concept of small signal coming from? Why do I need it? And what are the limitations of the small signal model? Let's try and understand it. One very important part is, please remember, which we forget, every model is an approximation. The real thing, the real component is different from the model. No matter how accurate a model you build, it's still an approximation. And therefore, many times what happens is, and we build a variety of models. Even for a diode, we have a simple model, we have a little bit more complex, and you can build maybe 6 different types of models of a diode. And each model is valid under certain situations. So what happens is, many times we forget that where to use a particular model. Each model has a range of validity. If you use a model beyond its range of validity, it's going to give you wrong results. So when we use a model, we should know where is it applicable and where is it not applicable. Okay, that's very important. One of the major errors in analysis occur because I've deployed a wrong model. The model is not applicable there. Okay, so although we remember the model, for example, your 0.7 volt model of the diode, right? So we know that we are approximating the diode by 0.7 volt. What if I apply a voltage here which is 0.6? What would happen? You replace the diode by a 0.7 volt battery, and I apply a voltage of 0.6, it would appear as if the diode is the source of current. The diode would start driving the current here. Obviously, it's not valid. When the voltage here, Vs is 0.6, and you approximate the diode by a 0.7 volt battery, that model is not applicable there. It's going to give you all wrong results. Okay, so we have to know where to apply that 0.7 volt model and where not to apply. Okay, so that's very important, and sometimes we miss that, and we start getting weird results. Okay, anyway, so let's go forward with our discussion related to the small signal model here. The story of the small signal model begins with what we call as incremental circuit analysis. You might have seen this slide earlier also, but let me start. Set the story here. So we have, we can take any example. So we have a circuit like this, arbitrary circuit. We have a circuit like this with some voltages and currents and all that. And let's say we've already analyzed the circuit once. We've already analyzed the circuit once, which means we have the value of the current and we have the value of the voltage available to us. Now, as you know, when I'm designing a circuit, that's not the end of the story. For example, I may have an interest in knowing that suppose I change the value of Vs by a small amount, by a little amount. How would my V naught change? Or your interest may be in knowing so what we are saying is we've analyzed it for whatever values that are given here, we've obtained a value for V naught. Now I want to know that if I change Vs by a small amount, by how much will V naught change? Or you could ask the question, if I change R1 by a certain amount, let's say if R1, I change it by 10%, how much will V naught change? Or if my current decreases by a certain amount, small amount, how much will the V naught change? So that's the question we are asking, and that's why I'm calling it incremental circuit analysis. Our interest is that I've changed something. I've created an increment in either voltage or increment in resistance or whatever it is in the circuit. I've changed something in my circuit. And I want to know, as a result of this particular change, how much does my, let's say, this voltage change and how much does this current change? So we are interested in changes. Given an increment in something, we want to know how much is the increment in something else. So interest is not in the absolute value. I'm not looking at what is the absolute value of V naught. I'm looking at what is the change in V naught as a result of change in Vs1. All right. So, for example, in this case, what we are asking is, say the voltage here changes by 10 millivolt. And we are asking by how much will the output voltage change? Okay. When we are asking questions like this, what we are doing is, we are doing a incremental circuit analysis. We are talking about increments in voltages and currents. Okay. Now, let me show you. These are results from simulation. Here is a circuit. I have a 1 volt source, resistor, arbitrary circuit with arbitrary values here. Resistance is 8 ohms here, 8 ohms here, 2 volt here. Current is 4 amperes here. Right? For 1 volt, the value at this particular node comes out to be minus 14.5. Okay. Now, one possible way of doing this is, as I said, I want to change Vs1. So in the next case, I change Vs1 by 10%. So we change it from 1 volt to 1.01. We have changed it by 10%, and we analyze the circuit once more. And we analyze the circuit once more, and we find that the value of this particular node is minus 14.495. Okay, which is the output voltage here. So if I were to ask the question, how much is the change in output voltage here in response to a change of 10% in Vs1 here, then what I would do is I would take this value, subtract it from this particular value, and get an answer which is 5 millivolt. Okay, that's one way of doing it. You analyze this particular circuit, you have an expression or whatever it is, you get the value of this particular voltage here. You analyze it once more with a different value of Vs1, you get another value here, you subtract the two, and you get the value here. Can you see a problem here? Yes, I can do it. There's no problem. I mean, in principle, it's giving me the answer. But can you spot a difficulty with this one? To get the answer, are you seeing that I have to make my calculations accurate up to third decimal place? To the third decimal place, if I don't do my calculations to the third decimal place, I'm not going to get the right answer. So this approach that you are seeing here, I have to, whenever I'm doing my calculations, I can't just do it to the first decimal or to the second. I have to do it to the third decimal place. The calculation here to the third decimal place, the calculation here to the third decimal place, and then subtract it out and then get the answer. Suppose this were not 1.01. This was 1.001. What would have happened? Instead of the third decimal place, maybe I would have had to do to the fourth decimal place. And this seems sort of ridiculous. I mean, I have to do such an accurate analysis of here and such an accurate calculation here to get this particular number. Incremental circuit analysis says you don't have to do that. There's a simpler way of doing all of that. You don't have to calculate first V0 due to 1 volt and then again calculate V0 due to 1.01 and then subtract it out. Don't do that. It will get you the answer, but it's far more difficult. I mean, it will take you, far more accuracy to get the right answer. A simple way of getting the answer, as all of you know, this is a linear circuit. I can use superposition. So earlier we had VS1 and it was giving me V0 here. We know what V0 is. Now we've added another source, delta VS1. And I want to know how much is the change here. So you know superposition tells you that now that I have two sources here, superposition tells you that the final value V0, final value whatever V0 plus delta V0 is, first you calculate V0 due to VS1, VS2, IS and all that, those sources. And then you calculate delta V0 due to only this particular source. So you can consider sources one at a time and calculate what is the output voltage here. So superposition tells you that it's a linear circuit. It's very important that it's a linear circuit. I can use superposition to calculate the effect of delta V0 due to this delta Vs. And when I do that in superposition, I have to remove the other sources from my circuit. When I want to find out what is this delta V0 due to this source here, delta Vs1, I remove all other sources from my circuit here. Removing means what? I short the supply, the DC here. I short this particular one here, short it out. I open this and we get a simple circuit here. This is the voltage that results only from this particular source. And that's very simple. Delta V0 is delta Vs1 R2 by R1 plus R2. And it gives me a precise answer of 5 millivolt. Exactly the same answer that I'm looking for. So I use superposition and I calculate what is the effect of delta V0 as a result of delta Vs1. And superposition gives me an answer. I don't need to now, for example, I don't need to do it at that level of accuracy to get the answer that I'm seeking. Okay? So for a linear circuit, I can use superposition. But if it's a nonlinear circuit, if I had a nonlinear element, I had a diode, or I had a bipolar transistor, I had a MOSFET, I have nonlinear, superposition is not valid. I can't apply superposition. So I have to look for something else. How do I, if one of these elements, let's say it was a bipolar transistor sitting there, I can't do that. I can't say that the output voltage, first I can consider due to all these sources, and then consider due to only this particular source, and then I can add up and get the final right answer. I can't do that. Superposition is valid only for linear circuits, when I have linearity. Anyway, another way that I can get this particular answer is similar, but in the following manner. Just illustrate to you an alternative way of arriving at the same answer here. So as you can see here, what we have done is this particular circuit is there. We have described this particular circuit in terms of these equations. Vs1 is I1 R1 plus V0. That's this part here. And I1 that you see here is equal to Is. KCL here plus V0 minus Vs2 by R2. Straightforward equations. So that's for this circuit. Next, what we are saying is we are changing Vs1 by a certain amount. So when I change anything in my circuit by a certain amount, all the voltages and currents in general would change by a certain amount, right? So if I change my Vs1 by a small amount, the change is described by a small letters here. So change is Vs1. What I would expect is that the current here I1 will change by a small amount I1 here. The voltage here will change by a small amount V0 here as a result of these changes. So the equation 1 is still valid, except that if I have changed this, then I1 also changes and V0 also changes. That's what we have written here. Similarly, as a result of this change, this I1 changes here. Is is a constant, obviously doesn't change. This V0 will change by a small amount V0 here. Vs2 is a DC voltage which I'm not changing, so I keep it as it is, and R2 as it is. Right? So we get these 3 and 4 here. Now what we can do is 3 and 4, we can subtract 1 and 2 from 3 and 4 and get these equations. Vs1 is I1 R1 plus V0. Note the small quantities here. This and I1 is V0 by R2, and we can combine them up and say Vs1 is I1 R1 plus I1 R2. Now, what is the characteristics of these set of equations? These equations are talking about only changes, only increments. And increment, see this small Vs1 is increment in Vs1. The small I1 is the increment in volt in the current that is flowing through that particular element. V0 is only the increment. So now this set of equations that you see here is only talking about increments. Increment in current, increment in this voltage, increment in that voltage is only talking about increments. It's not talking about the absolute value of the current here. It's only talking about increments here. Now I made a statement earlier that whatever circuit I have, I can transform it into a set of equations and solve it. Now, these equations that I have here, I can transform them back into a circuit, right? If I can take a circuit and transform it into an equation, set of equations, then you would also expect that those equations, I can transform it back into a circuit here. So for example, this thing that you see here, this set of equations which are talking about increments in currents and voltages, I can transform it back into a circuit here. These equations basically come from a circuit, this one. What is the thing about this particular circuit? This circuit is talking about increments. Increments in current, increments in voltage, increments in this. So we call such a circuit as an incremental equivalent circuit. Where is it derived from? It's derived from the original circuit. It's derived from the original circuit, but we are calling it as incremental equivalent circuit. But why? Because it gives us relationships between changes in currents and voltages. It's not talking about absolute value of what I1 is and what V0 is and all that. It tells me changes. If I change Vs1 by a certain amount, which is the all small quantities are changes. So it tells me if you change Vs1 by a small amount, Vs1 here, current would change by a small amount I1, V0 will change by some amount V0. This V0. Note, I'm talking about small, but because this is linear, in fact, I can change it by any amount. I shouldn't use the word small here. I mean, the change could be, I could change, if let's say this Vs1 is 1 volt, I could change, this change could be 1 volt also. There's nothing in these set of equations which is telling you that you can't change it by 1 volt. There's nothing small as such about it right now. Because it's linear, it doesn't really matter. I can change it by 1 volt. Not only that, if Vs1 is 1 volt, I can change it here by 10 volts. So increment right now, please be clear that when I'm talking about incremental equivalent circuit, there's no notion of small as such. I use the word small, but there's no notion of smallness at all in this analysis. I can change it by any amount that I want. There's nothing in these equations which is preventing me and telling me that you can't change it by, you have to change it only by 10% or 20% or whatever. You can change it by any amount that you want. All that we are saying is, we are talking in terms of changes, increments. An increment in Vs1 results in an increment in current here, increment in voltage here, and we can get the answer by making an incremental equivalent circuit. Right? So the thing is, if you're interested in, if in your analysis, you will require that what happens if I change Vs1 by a certain amount, what will happen to the change in V0? If you're looking for those kinds of answers, those answers you can obtain by building incremental equivalent circuits. They will give you those answers in a simplified manner. Okay? So what we have done is shown you maybe through a particular example the importance of building incremental equivalent circuit. How do we build incremental equivalent circuit? Well, a general method of building incremental equivalent circuit is build incremental model for every element in the circuit. An incremental circuit is made up of incremental models of the circuit elements. Okay? Example. So, just some terminology. So, now when we analyze a circuit, when I use a capital V and a capital X, it refers to the nominal or the base value, often a DC. Vx, small v, small x refers to an incremental value. The net value is made up of, if you're interested in absolute value, it would be made up of some base value plus the incremental value. Okay? So normally you find that in my circuit I have some DC voltages and currents. So the base value or the nominal value is a DC. Then in amplifier especially, we'll add an AC or some signal that we'll add, small signal that we'll add or whatever. So this will often be an AC, but it could be anything here. And so remember this this thing here. Capital V, capital X is the base or the nominal value of voltages and currents in a circuit. This refers to an incremental change. If you want the absolute value, it would be made up of whatever was the earlier value plus whatever is the increment. That's the absolute value or the net value of voltages and currents. So in all our analysis, sometimes we are talking about this. Sometimes we are talking only about this. Sometimes we are interested in the net value also. Okay. So often a confusion occurs and mistakes occur in mixing these two. When I'm seeking an answer to capital V, capital X, base value, and in that, if somebody mixes this particular one, then errors will creep in. So please keep that in mind, and we'll emphasize it at various points. Okay. So as I said, if you're looking for answers such as increments in voltages and currents, the way to do that is to build an incremental equivalent circuit of or whatever circuit that you already have. And you build incremental equivalent circuit by building incremental equivalent models of the elements here. So take resistor. Resistor is V is I times R. Right? That's a normal model of a resistor. Now I want to build a incremental model of a resistor. What does incremental mean? Let's say I change I by a certain amount. The voltage then will change by a certain amount. So let's do that. If I change I by a certain amount I here, the voltage V will change by a certain amount V here. Note that the changes are denoted in small letters. What incremental model means what? What is the relationship between the increment I here and the increment V? What is the relationship between incremental changes in current and incremental changes in voltage for that particular element here? So that's very easy to write down. V equal to IR. It's simply that. What does it mean? That the incremental model of a resistor is nothing but a resistor. So resistors will not change. When you're building an incremental model of a circuit, wherever you see a resistor, the incremental model of a resistor is nothing but a resistor of the same magnitude. Nothing changes. Okay? So resistor is a resistor of the same magnitude. Nothing changes here. What about a capacitor? Well, we can do the same thing. I equal to C dV by dt. We change the voltage across a capacitor by a certain amount V here. The current would change by a certain amount I here. The relationship between incremental current and incremental voltage is still the same. I equal to C dV by dt. Capacitors also don't change. They remain the same. And this same thing is about an inductor. Inductors also don't change. Capacitor is the same, inductor is the same, resistor is the same, nothing changes there. Okay? A voltage source. Voltage source means V is a constant. So V is a constant means any increment in this is zero. There cannot be an increment in a voltage source. So a voltage source becomes a short. V equal to 0 means we have an element now across which voltage is 0. So it's a short. So voltage sources, when I'm doing incremental circuit analysis, voltage sources become shorts. Because the model of an incremental model is V equal to 0. It's a short. Current source, I equal to constant. There cannot be any increment in current. So small I is 0. So current sources become open circuit. Right? So these are some of them, and then we can build incremental model for other elements also. The procedure is the same. The procedure is you change the current by a small. Again, I have to guard myself. Many times I've used the word small. There's no small as such right now. It's only talking about in an increment. If you change the current by an increment I, the voltage changes here, and all that you're looking for is what is the relationship between incremental change here and incremental change here. So for any element, you can do that. That's a general method for getting incremental model of whatever element that you're looking for. And then what you do is, whatever circuit you're given, you build an incremental model. So we said resistor remains a resistor, so we've kept it as it is. R2 will remain as it is. Voltage source becomes a short, so we've removed it. And current source becomes an open, so we've removed it. And so you end up with a circuit like this. And this also is a short here, and we've added an incremental. We are looking for an incremental change in VS1, so we added a source here, corresponding to the changes here. Okay, And so we have an incremental equivalent circuit, and of course you can get the answer very quickly in terms of what you're looking for. So when you want to do incremental circuit analysis, and there are lots of places where you're interested in doing that, what you do is build an incremental equivalent circuit. And from there you'll get all the answers that you're seeking in a simplified manner. Note there's no approximation involved. I'm not making any approximation. The answer that you'll get is as accurate as any other method. No approximations involved anyway. And there's nothing about how large an increment or how small an increment you can take. You can take anything that you want. Because it's a linear circuit, it doesn't matter. Okay? Increment can be small, increment can be large, it can be anything. I've only talked about, we'll give you as an assignment, what happens if R1 changes by an amount, delta R1? What do you do there? Think about it later on, okay? Fine. Let's now introduce a nonlinear element. So in my circuit now, as you can see here, I replaced that R2 and all that, and I've introduced a nonlinear element X. Some nonlinear element whose characteristics is given by Ix is k Vx squared. So now again, now note the thing is, I'm looking for how much is, so I have DC here and all that. I'm looking for that how much AC voltage do I get here? How much AC voltage I get here at the output? AC voltage is over here. So I'm looking for that. So in principle, there's no problem. I can write KVL, KCL and all that. And I have a model for every element. I can transform the circuit into a mathematical set of equations, solve them up and get the answer. So the traditional method is valid, except that you'll find that it becomes complex to do analysis. And we're looking for an alternative way of getting answer, which is simpler. Okay? So what we do is, what we'll try and do it is, we want to know how much is the AC voltage here, okay, at the output. So what we'll do is, we'll think of this AC source as an incremental change. We'll think of it as an increment. We'll think of, let's say I have a circuit which does not have this AC source here. I have a circuit with only VCC, R, X, IS and all that. Suppose that circuit I've already analyzed. And I know what is the value here, and the value would be DC, right? Everything else is a DC. Now I think of this extra source as an incremental change that I've introduced in my circuit. And I would like to calculate what is the incremental change. So I want to analyze this particular circuit from the viewpoint of an incremental change. I look upon AC as an incremental change in the circuit. Some change I've introduced in the circuit. And I want to get an answer of what is the incremental change in V0 here in relationship to this. So how do I do that? Well, as we said, if you think of this as an incremental, then you have to build an incremental model for everything else. So, this is the incremental change, so I retain it as it is. DC will become short. Resistor will remain as it is. Resistor. Current source becomes an open circuit here. And what do I need when I'm building an incremental circuit model? I need an incremental model for the element X. I have to find out what is the incremental model of element X. And once I find the incremental model of element X, I put it here, and then I'll get the answer that I'm looking for. Analyze it and you'll get the answer. Note that because our interest is in this AC, the circuit that I have to analyze is much simpler than this. Okay, much simpler. That's where the advantages come in doing incremental. Anyway, let's try and build the incremental model of this element X. How do we do that? This is the general relationship of this particular element. Ix, current flowing, is K times Vx squared. Our method of building incremental model is, let's change this. Vx now is made up of some base value or nominal value plus an incremental value. Okay, we change this. In red is shown the incremental change. So this is the nominal value here, whatever is the DC or whatever base value of the voltage across it, that is there. And this is the incremental change in Vx. And this is the normal DC current flowing through it. And this is the incremental change in the current here. And what are we looking for? We're looking for a relationship between these small quantities here, incremental changes. So let's do that. We can easily simplify this here, and you get the following here. Ix here is k Vx square 1 plus Vx by capital Vx minus 1. That's the model that you get here. Now, do you notice something? This is the model, fine. But to calculate, to use the model, what do I need? K is a constant. What do I need? I need the DC value, right? I need this base value, Vx here and Vx here. Without the DC value, I don't have this particular model. So when the moment you get a nonlinear element and you build a incremental model for this one here, to use the incremental model, you would require the base value. What was the DC voltage across that particular this thing here? So before doing the incremental circuit analysis, you have to do an analysis without this AC source, remove the AC source, do an analysis of this particular circuit, which will give you the capital Vx that you see here. After you've done that, then you can build a incremental circuit model here, plug it into this particular one, and get the answers that you see. You'll get the answers. That's the procedure. So the moment you get a nonlinear element, you have to do a first analysis of the circuit without the incremental change. Okay. Now this equation, no, because I've used a nonlinear element, the model is also nonlinear. Now the concept of small signal comes in. See, any nonlinear element that I have complicates my analysis. Now there are a large variety of situations where you find that yes, I have a nonlinear element, but the incremental changes that I'm talking about are small. That the AC voltage that I've applied here is a very small AC voltage. Right? So if it's a very small, if the increments, now I'm bringing in the notion of small. If the incremental change is small, then you know that any nonlinear element, if you make small changes, you can approximate it as linear. Okay, so that's what we are going to do. Nonlinearity makes the model difficult to use. So, and if the signals in my circuit and incremental changes are small, we use approximations to make it linear. So in this case, we have a nonlinear model, incremental model which is nonlinear. We make it linear. Why? And we use the approximation as small signal approximation. That this change that you see here, Vx, will say that this Vx is much smaller than the base value. So we are making a very important now approximation which we call as the small signal approximation. The incremental change in Vx that you see here is much smaller than the base value, the DC value. If that is true, then it's if I make this approximation, then it's very easy to simplify this into this particular form. All I do is I expand it and I ignore the quadratic term. If the value of the small Vx is small here, quadratic term would be much smaller and I can neglect. And so we can approximate this one by this particular expression. And this now note, what is the relationship between small ix and small Vx? It's a linear relationship. Everything is a constant. K is a constant. This is also a constant. Vx is some DC value which is a constant. And so I can write this as Ix equal to Vx by Rx. So my element X under small signal approximation becomes basically a resistor. A resistor whose value is 1 by 2K times Vx. Now the notion of, so when I built an incremental circuit model of this nonlinear element, the incremental model is also nonlinear. Now I say that the increments are small in nature. The increment is small in nature here. I make this approximation. And with this approximation, my element then becomes linear. Element becomes linear, and in this case, it just turns out to be a simple resistor. So now what I do is, now when I'm building a small signal model, so it's not just an incremental model of this particular circuit. Now we are saying a small signal model. So when I say small signal model, it is understood that we are building an incremental model. And further, we are also talking about increments which are small in nature, so that in non-linearity we can sort of ignore and any nonlinear element we can linearize. And in this case, then we obtain this particular expression here, and we can get the answer that we're looking for. So if the voltage that you see here is small in nature, then I can get the answer V0, which is very straightforward. V0 is still Vs Rx by R plus Rx. So what is a small signal model? First of all, small signal model is a incremental model of an element. Secondly, it's an incremental model of an element where I make the approximation that the changes across this are small in nature, and therefore we ignore all the non-linearities that are there. We keep only the linear term. Now, a notion, you must be asking, how small is small? Is 1 millivolt small? Is 10 millivolts small? Note that now the answer that you will get is, because we have made an approximation, the answer that you will get is approximate. It will not be the final, the accurate answer, because we have taken a nonlinear element and ignored the higher order terms and kept only the linear terms here. So it's an approximation now. It's an approximation now, and the answers are also approximate. The answers will be inaccurate. How inaccurate it will be would depend on how large the signals are. Okay, so let me show you. So let's raise this issue. How small is small? Well, it depends on how accurate an analysis are you willing to do. How much errors can you tolerate? If you can live with 10% error, well, the smallness would depend on that. Okay, so as an example, this is the accurate model. Incremental model, this is the accurate. And we have approximated it by this one. Now we can easily say how small is small here. Note, let's say my base value is 1 volt. My base value of this DC value is 1 volt. If I use, if the Vx that you see here is 20 millivolt, the error between this model and this model is 1%. So I put Vx equal to 20 millivolt here, it predicts a certain value of current here. I put 20 millivolt here also, it predicts a certain value of current here, and we look at the error. The error is 1%. If I put 0.22, the error is 10%. If I put 0.5, the error is 20, 1, the error is 33.3. So if you're asking, what do you mean by small? Then the question that I would ask you is, how accurate an analysis do you want to do? Can you live with 10% error? If you can live with 10% error, it means the Vx that you see here has to be smaller than 0.22 volt. As long as you are less than 0.22 volt, the error in your model is less than 10%. If you say, no, I want to do very accurate analysis, I'm looking for very, very precise numbers. If you're looking for 1%, then I would say, well, your model is valid only for Vx less than 0.02. You can only use this model if the voltage that is there across that particular element, incremental voltage across that element, is less than 20 millivolt. Then your model would be accurate. I mean, the accuracy is within less than 1%. So how small depends on how much error can you tolerate. That's where I said sometimes we are not looking for a very precise answer. I'm not looking for an exact value of current. I'm doing my analysis to obtain a simple expression. And that expression would be used to understand how the circuit behaves. So my goal is not so much as a precise, so I'll is valid maybe even at 0.22. I'm looking for an error. Many times the analysis that we'll do, if it's accurate within 10% error, we take it as fine for an initial level analysis. So for this case, I can apply a voltage which is Vx as large as 0.22. 220 millivolt, it would work fine. Okay. Now, in practice, what would you do? Say I have a circuit like this. I don't know how much is the small Vx here, right? I don't know whether I can apply. Even with 10% error, we know that with 10% error, we need Vx as 220 millivolt. So what I do is with whatever sinusoid is given here, I apply this particular model. I apply this particular model here. And once I apply it, note that I will get the voltage across this, right? The voltage across this particular element, small Vx that you see here, is nothing but V0. I'll get V naught. And then I check, is my V naught less than 220 millivolt? If it's less than 220 millivolt, I know that I've done my analysis within an accuracy of 10% and it's fine. But if it comes out to be 0.5 volt, then I know, well, I can't apply this particular model. Okay? So the only way, one of the ways of checking it is use the model, deploy it, analyze it, find out what the values of the voltages, whatever these are, and check whether this particular voltage is small enough for your accuracy or not. Okay? So that's the meaning of a small signal model. What is a small signal model? It's an incremental, first of all, it's an incremental model of an element. And what we do after that is we assume that the voltages and the currents are across it are small in nature so that we can linearize. We can ignore second order and third order and quadratic and all those other higher order terms we can ignore and keep only the linear part here. And by that we build a small signal model. What is the advantage? We have seen the advantage of incremental circuit analysis. The advantage of small signal incremental circuit analysis is the circuit becomes very simple. It's, this element is only a resistor now. And we can very quickly analyze and get the answers that we're looking for. Otherwise, the model is nonlinear, the analysis will become far more complicated. Okay? And in many places, as I said, the signals that are there in my circuit are small in nature, and therefore, when we do analysis, we get answers which are not only simple, but are fairly accurate as well. You don't lose too much accuracy also. Okay? So let's stop here. In the next lecture, we'll see some more examples of nonlinearity, and we'll see how to build build small signal models of elements. And then we'll go on to PN junctions and BJTs.